Hello viewers, welcome back to another section of my tutorial. In this video, we have thevenin's theorem, a problem to solve using thevenin's theorem. So this is a complex bridge circuit which you've been asked to find the current in the 2.4 ohm resistor using thevenin's theorem. So that is the problem we have here. So we have to use thevenin's theorem to find the current through this 2.4 ohm resistor in this circuit. Kindly subscribe if this is your first time you are visiting this channel. Please turn on the notification button so that you get notified whenever I post new videos. Kindly watch the video to the end so that you get every aspect of the video. So let's see. Thevenin's theorem is a theorem that helps us to simplify circuits by finding current in some resistors of a bigger circuit. So without wasting more time, let's see how we can simplify this circuit and go about finding the current through this 2.4 ohm resistor. So to apply thevenin's theorem, we need number one, what we call the thevenin's voltage. So thevenin's voltage. Then number two, we need the thevenin's resistance. Thevenin's resistance. So these are the two major things we need before we can find the current through this resistor using thevenin's theorem. So first of all, how do you find the thevenin's voltage? To find the thevenin's voltage, the rule is remove the resistor which we are considering in our question or in our problem. Then replace this resistor with an open circuit voltage. So that is what I'm going to demonstrate to you right now. So I'm going to redraw this part and show you how we can draw it. So we will start our drawing here. So this is, so let's start it again. Then this is the 3 ohm part. So when we come to the 2.4 ohm part, there will be an open circuit. So there will be an open circuit. Then that is where we put the thevenin's voltage to. So at this point, I'll have this one here coming in, then to this side. Then I'll have my middle side here to this side. So here we replace the 2.4 ohm here with an arrow indicating direction for our thevenin's voltage, and we introduce a capital V, then TH here, indicating that this section, the resistor here has been removed, and now we have the thevenin's voltage represented here. Then we move on drawing the other parts of the circuit. So this is how we are going to place this whole circuit. So now this side is going to be our 3 ohm. Here is our 3 ohm. This side is 5 ohm. Then this is 3 ohm. So this is only the bridge side. Now let me redraw this whole part so that we see it. So let me draw it boldly here. I'll have this side, sorry. So this is the open circuit. Then it will come to this way to this side. And I have my middle here, 3 ohm. Then this side goes to this, then come into the 10 ohm, the 10 volts. So here's the 10 volts. Then this one will go to the 3 ohm. Then this side will join to this. So here I have my VTH. Then the VTH has a direction moving up. That is it. So it is going up. Then at this I have 3 ohm here. 3 ohm here, 3 ohm here, then 5 ohm here. So this is our circuit now. We've introduced the Thevenin's voltage. The next thing to do is to find the Thevenin's voltage. We need a value. So how do we find it? So pay attention to this portion as we go through finding the Thevenin's voltage. So now let's see. Once you have the Thevenin's voltage here, you have a complete circuit. There is a voltage source. Surely there should be a current. Now this voltage source will produce a current called IT, that is the total current from the source. So you have our IT here. When the IT reach this junction here, you realize that there will be what? Splitting. It's going to divide by KCL, Kirchhoff's current law. So at this point, you're going to have our I1, but you realize that the I1 will move and it will enter to this side, right? It will move. The reason why it will skip this side is this place is an open circuit, so it's assumed that there is a voltage here by Thevenin's theorem. For that reason, there is no continuity from this side to this side. Please take note with this point. There is no continuity from here to here, even though there is a voltage source here. There is an open circuit, so here there is nothing here. So when the current passes through here, it will come down here and continue its journey by joining its compartment here. So let's see, the I1 that will be divided will pass here, then it will come down. So let me introduce it here. That will be I1, right? Then the I2 will come straight down here. Then upon reaching here, you know that here's the I1 coming. Then our I2 will come here. So our I2 will come here to come and meet this I1, then move as what? Our IT. So our IT will come here back again, IT, right? So let me introduce my I2 somewhere here, because it's going to split here. We have I1, so I can make this place to I2 for also consideration. So here, instead of IT, I can make this side, the one emerging out of our network, I2. So here is going to be I2. So the current operation here will divide into I1 then I2, but this side I can also make here I2, then I will clean this side. The I2 and the I3 are just variables you are assigning to your current. So the current passing through here is not the same coming here. You realize that this current emerging out here is the same as the total current was IT. So now let me make my I2 here for simplicity. So this is my I2 here, and you realize that this place will then be IT, that is our total current, because this and this will join and it will continue the journey. So I have my I1, I2 will meet to IT, then it will pass and it will come out. This is a simple layout I have shown you. Now our goal is to find our VTH, Thevenin's voltage. Don't forget, whenever you are doing calculation, ask what is your goal, what do you want to find. You want to find this Thevenin's voltage here, VTH. So to find VTH, we take a loop with the VTH in it, so that we will follow that loop and find an equation. So in this loop, I can do this. This is my VTH. This is the direction to move this side and come here. By Kirchhoff's loop law, I can make this here. That is, I'm going this way. So you realize that my VTH, which I have here in an equation form, will be equal to, this VTH here will be equal to 3I1. That is the voltage drop across this 3 ohm, 3I1 plus 5IT. 5IT. That is plus the total current emerging out here. So when I get my IT, when I get my I1, I'm good to go to find my VTH. So now the goal is no more for the VTH, but rather I1 and IT. How do we find I1? How do we find IT? So let's come back to our circuit. Where is IT coming from? From the main source. To get IT, you know that IT, which is the total current, is always equal to the total voltage VT over the total current IT. So once you have this, we are simple, or we are moved here. So from here, what's our total voltage? That is 10 volts. Sorry, here is total resistance, sorry, because you are finding current. So our total voltage is 10 volts all over total resistance. How do we find the total resistance? That is the next where we are going. So see, when you have this circuit, let me show you something here. When you have this circuit here, you have one resistor out here. That resistor, when you reach here, you realize that this 3 ohm here, then this 3 ohm here are in series, because there is a continuation, the same current passes through. So this and this will be in series together, they will be in parallel with this. The whole resultant will then pass here. You see, we follow the path of the current to determine whether the resistors are in series or not. The same current will pass through this and this, hence they are in series. But you realize that a different current will pass through here, then this combination will be in parallel with this. The whole combination will then be in series with this. Since the returning current will finally pass through here, there is nothing here. For that reason, this 3 ohm here we have here is in series, plus these two resistors are what? Also in what? Series, then in parallel to this. So you have this 3 ohm here in parallel with the series connection inside. So this 3 is parallel with this and this, then this whole thing will finally be series towards the 5 ohm resistor. So this whole combination here, as you have here, it will finally be what? In series with this 5 ohm resistor. So this is our simple total resistance for finding our Thevenin's voltage. So now let's move straight finding our Thevenin's voltage. So here we are finding the total resistance first. 3 ohm is parallel to 3 plus 3. So let's do the series aspect. 3 plus 3 is 6. So we are going to have 3 plus 3 being parallel to 6. Then the whole being in series with 5. This simple mathematics here. Then from here you realize that this and this will be 3 times 6 over 3 plus 6 plus 5 plus 3. What are you getting? You are going to get here to be 9 over 3 times 6 is 18 over 9, that is 2. So 3 plus 2 plus 5, and that is giving me 10 ohms. That is 10 ohms. So here I'll get my total voltage 10, total resistance will be 10. Hence my IT is simply equal to what? 1 ampere. Now I have my IT for this side. How do I find my I1? Let's come back to our equation, our circuit. In the circuit here, you realize that once you have this here, we want to this total current reaching here, you realize that upon reaching here it's going to divide into this form. The sum will pass here and it will come here, then this part will meet it here. So what we are going to observe is we want to apply the current division rule. For that reason, the total current, which is 1 ampere, upon reaching here will split. But current division rule always involves two resistors which are in parallel. So you realize that this whole series connection of the 3 ohm and the 3 ohm, they are in parallel with this 3. I can open up this point here for you to see it well. So we are getting something like this, and this will move to the 3 like this. So here's 1 3 ohm, here's another 3, and these two combination, they are all, you get it, one is here, there is a node here, and that node is actually pushing out to a different portion. Then this whole 2 is in parallel with another resistor here. So this and this will give me 6, and realize that I'm going to get a straight one. That is, I'll get something like this. Then that one will come to this. So here will be the 6 and here will be the 3. That is what I want to show you here for you to understand. So let's move forward. So once you realize that the total current was placed according to this 3 plus 3, and also here we can use the current division rule to find our I1, because the I1 is passing through what? The 3 and the 3, which is the 6. And the current division rule, where the current is passing, the resistor which the current is passing, we don't use that one, we use the opposite. So the opposite, this one, over the total resistance times the total current. So now you realize that our I1 will simply be equal to the 3 which the current is not passing through over the sum of the others, that is 6 plus 3, that is 9, times our 1 amperes, and that is giving us 3 over 9 amperes. So since we have our I1, we have our IT, we can find our VTH. So our VTH here is simply equal to 3 open bracket I1 3 on 9 plus 5 open bracket 1. Realize that 3 times 3 is 9. Here will give me 1. Therefore my VTH is simply equal to what? 1 plus 5, and that is 6 volts. And that is simple. That is finding the VTH. Now, from the beginning, I made mention that to find current through a resistor using the Thevenin's theorem, we need two things. We need the Thevenin's voltage as well as the Thevenin's resistance, right? So now let's see how we are going to find the Thevenin's resistance. That is also a different approach. So please watch the video to the end as we follow through the steps. So from here we have to redraw this circuit, taking out the section. So I want you to observe it carefully. So now see, to find the Thevenin's resistance, what they are saying is you remove the resistor which you want to find the current passing through. You remove it away, then you replace it with our Thevenin's resistance RTH. So see, you still have this, then you have this, you have this, you have this, 5 down here, then you have this. So I left to make it open here, so let's go back. So completing this side, I'm going to have my open circuits, yes, then this side will join, this side will join, I'll have this side. And take note, whenever you are finding the Thevenin's resistance, there shouldn't be any power source. Every voltage source should be a short circuit. You should just create a short circuit for any voltage source. Then for a current source, you open it up. So let's see, I have my 3 here. So once I have this, I have my 3 ohm here, I have my 3 ohm here, I have my 3 ohm here, I have my 2.4 ohm here, but I have removed it and I have placed my RTH here. Then this place is 3 ohm. Now to solve or to find our Thevenin's resistance, what you are going to do is you have to label the terminals. So let's see. So let me draw this side for a new page. So we have to make here A, here to be B, here to be C, and here to be D. And these terminals are going to guide us because the Thevenin's resistance is saying that we should find the resistance between this and this. So we open this up, like you trace it and open it up this way. Then you open this one as well. Then the rest will follow. So let's see how we open it up. We have the A and D as the terminals where the RTH is. So you make your bigger A here. Then you make your bigger D here, right? So once you have your bigger A and your bigger D, this is where the terminals are. So your 0 terminals and your terminals are here. You want to open it up. You are finding the effective resistance within these terminals. So you have this A, and you realize that this A here is moving towards C, right? So this A here is moving to C. So this A is moving to C. So let's say C is somewhere here. Then you know that the same A is moving to D, and that is what we have for the open. So now let's see. From C, you are going to have D here too, moving towards another. We have another one here, 3 ohm. But let's observe it carefully. So I place C up here because A is moving to C. Then C2 is moving towards B. Then B will move towards D, right? So let's see. You draw another one here, like this. So C to B, and C to B, A to C was 3 ohm. C to B is 3 ohm. A to, from here to here is A to B. A to B is also 3 ohm. So meaning I'll bring it down here. It's also 3 ohm here. Then now I'm left with C to D. Where is C to D? From C here coming down to this D, I have 3 ohm here. So it also goes in like this to the terminal. Then it comes down, D to B is what? 5 ohm. I left it. So this side will come as what? 5 ohm. So right now this is what we are having. I have my 3, 3, 3. Then from C to D is also 3 ohm. Then I want to find the total resistance here. You realize that I have this and this to be a delta. Hence I have to convert it to star before I proceed. To convert it to star, create a resistance in between any two. So between A and C, I'm creating one here. Between A and B, I'm creating another one here. Then from C to B, I can create it anywhere here. You get it? So here is my, let's say, A, B, and C. What are the values of A, B, and C? What are the values of A, B, and C? To find out A, B, and C, what you are going to do is to convert from delta to star. You are going to, so right now this resistor A here is in between what? This one, that is this 3 ohm resistor, as well as our what? So let's see. So each leg should be between two resistors. So this B is between this 3 and this 3. This C is between this and this. So I think this A should rather move this side because we need a resistor between this 3 ohm resistor. So let's see. This is 3 ohm and 3 ohm. We have C. 3 ohm here and this 3. That is what we are lacking. So I think that is where we are supposed to put one, not this. So let's see. So I'm going to clean this side so that we put one here. So that we put one here. So I'm going to have one here. Yes. So right now I have my A, then my B, then I have my C here. So my A is in between this 3 and 3, my B is between this and this, then my C is between this and this. Anyway, that is how we convert from delta to star. So what will be the value for A? You take the two resistors in which this new one is in between, then you multiply all over the sum of the rest. So let me multiply. I'll get 3 by 3 all over 3 plus 3 plus 3. So what is this? 3 times 3 is what? 9. All over 3 plus 3 plus 3, that is 9, and I'm getting what? 1 for all. So here, let's see how it's going to be. So I'm going to redraw it. Upon redraw, I'll have my terminal A moving to my 3. Sorry, my terminal A. So let me go back. So we are following this path. I have my terminal A coming down, then moving up to this, to our node, to our B here. Then let's see, to also move up to the A. So here's our A, here's our B, but they are all 1 1. So I'll write A, so I'll write my 1 here, my 1 here, then my 1 here. So here's my terminal A. Then this place will move and join. So this will join this, this will join here. So to redraw it well, I'll have this side coming down. For you to understand, that's how I'm following this section. We'll continue here, then this side too will continue here, and all of them will meet at the D. So already this is 3 ohm, this is 5 ohm. So this is 5 ohm, this is 3 ohm. Now let's see, this and this are now in series, and this and this are now in series. So let's see how we move forward. So here and here will be 4. So I have my A. Then this place will move to the 1. I have here, it will move up to be 4. Then this place too will move up to be 6. Then they will join to form the D. So 4, then 6, then 1. Then it will move up to D. So how do I proceed? So for the 4 and the 6, I'm going to have my total resistance because they are in parallel. So 4 times 6 all over 4 plus 6, and that is giving me 24 over 10, which is also equal to 2.4. Then I'll have my 1 here, so I'm going to get 1 plus 2.4, giving me 3.4 ohms for my. So this 3.4 ohm is equal to the Thevenin's resistance RTH. So my VTH from the question I had 6 volts. Then my RTH from our question I've solved to get 3.4 ohm. Now let's see how to find the current. So we need to draw the Thevenin's equivalent circuit, which says that there is a circuit whose source is the Thevenin's voltage. That circuit is in series with the Thevenin's resistance RTH. So here is VTH, and also in series with the resistor which we want to find the current through, R. And the current through this circuit is the current we want. So sorry, it's going to be this way. So this is not. So here, to find the current I is simply equal to VTH all over R plus RTH. So what's my VTH? That is 6, right? So I'm going to have my 6 all over 3.4 plus, and in the question we wanted to find the current through the 2.4 ohm resistor. So So we need to bring the 2.4 back again. So the 2.4 here, so the 2.4 back again, we need to bring it here. So 2.4, so 2.4. So right now I'm going to get 6 over 5.8, and now my I current is simply equal to 6 over 5.8, and that is giving me 6 . So our current is simply equal to 6 over 5.8. So we have to simplify this to get our final answer. So 1.034 amperes. Thank you for watching this video. Thank you for being with us. Please subscribe, like and share. See you in the next video.